Let me ask you a question. What should our first chapter cover? We are diving into permanent magnet motor design, but why are we designing it? What's the end goal we are aiming for? If the end goal is clear and inspiring, we will be motivated to take the necessary steps to achieve it. And in this case, designing a permanent magnet motor. So in the first chapter, we will focus on the end goal and gain an intuitive understanding of the working principle of PMSM motor, in other words, Permanent Magnet Synchronous Motor. So what's the end goal? Our end goal is to power a car with electricity. That's the ultimate goal we want to achieve. Now, how does car moves? The most fundamental requirement to move the car is to rotate the wheels. Currently, it is done by an internal combustion engine which requires petrol or diesel. Now, I have a question for you. If internal combustion engines are doing the job, what are the top 3 reasons to switch to electric vehicles? 1, 2, 3. Yes, you have guessed it. The first reason is the environmental impact. Electric cars produce zero emission, reduce pollution and the greenhouse gases. The second reason, the lower cost. Electric vehicles have lower maintenance and the fueling cost and often comes with government initiatives. Third reason is better efficiency and performance. EVs are more energy efficient and offer better performance with the instant torque and the smooth acceleration. Now that we see the excellent benefit of EVs, the question is, how do we rotate the car's wheel using electricity? We need the tools that take electricity as an input and produce a rotating wheels or a torque as an output. This tool is called a motor, which converts electricity into the rotational effort or torque. Now you might ask, what is torque? Imagine you need to open a nut. How do you do it? Tell me. First, you place a wrench on the nut and apply a force, mostly perpendicular to the wrench handle at some distance r from the center of the nut, right? This action generates a rotating effort at the nut, causing it to turn, and that rotating effort is nothing but called torque. The torque experienced by the nut is given by T is equal to R multiplied by F. If you double the distance, torque doubles with the same force, making it easier to open the nut. Conversely, if you halve the distance while keeping the force same, the torque is halved, making it harder to open the nut. A fixed force produces the most torque when the radius at which it is applied is maximum. Moreover, only force acting in tangential direction creates the maximum torque. If you apply the force to the left side, the wrench simply slips off and no torque is generated. This demonstrates the importance of the direction of the applied force. Taking this into account, torque can be expressed as T is equal to R multiplied by F multiplied by sine theta. Here, theta is the angle at which the force is applied relative to the radial direction. Let's validate this relation. You have likely noticed that the force applied to the wrench is most efficient when it is in the circumferential direction, that is, tangential to the circle centered on the nut, which is at the 90 degrees. From the above relation, sine 90 is 1 and torque is simply the product of force and the radius. Now the next question is, how does a motor works? Now that we know what torque is, which is nothing but rotating effort, let's understand how a motor generates this torque. Imagine a straight bar magnet with a small hole in the middle pinned to a table so that it can freely rotate. Take 2 more straight bar magnet, one in each hand, and bring both hands close to the pin magnet, making sure the poles are opposite with the slight gap between them. Now rotate both hands together while maintaining the gap. The pin magnet will rotate. Yes or not? Yes, the pin magnet will rotate. This is essentially how a permanent magnet motor works, with 2 key differences. The first key difference is the handheld magnet are replaced by coils wrapped around the iron cores, which act as magnets when supplied with the current. The second key difference is instead of physically rotating the coil, multiple coils wrapped around the iron core are equally distributed around the circumference. Current is supplied in the proper direction and the sequence to achieve the rotation effect. In this animation, I switch on the coil A with the current in such a direction that end A becomes south and end A prime becomes north, attracting the pin magnet and aligning it to coil A. Then I switched off the coil A and switched on the coil B, making end B south and end B prime north, realigning the pin magnet to coil B. This cycle continues. This switching on and off along with maintaining the proper current direction is managed by a smart electronic switch. Now here's a question for you. How do you increase the RPM or speed of the pin magnet? The answer is quite obvious. To increase the RPM, we need to switch on and switch off very fast. In other words, we need to increase the switching frequency while maintaining the proper direction of the current. Now I have another most important question for you. How do you increase the torque? Remember, torque is described by the formula R into F. To increase the torque, either force or radius or both need to be increased. Simple, right? Then how do you increase the force? There are two ways to increase the force. First method, stack another bar magnet on top of the first pinned magnet and add another layer of coils wrapped on iron core on top of the first layer. Now both pinned magnet experience the force, effectively doubling it. In general, force is directly proportional to axial length. Second method, place another bar magnet at 60 degrees to the first magnet. Instead of switching one coil at a time, start switching two coils. Hence, net force became twice. In general, force is proportional to the number of magnet poles placed at the circumference, meaning higher the diameter allows more magnet to be placed and hence increases the torque. Another obvious way of increasing torque is to increase the radius component in the formula. Now finally, torque is equal to R multiplied by F. Since force is proportional to axial length and the diameter, we can write torque proportional to R, and here F I am replacing with D multiplied by L. Now here R can be replaced by D by 2, right? Yes. So now finally the torque is equal to K multiplied by D square multiplied by axial length L, where K is the proportionality constant. This also answers the question of what should be the size of the motor to produce the required torque. In other words, what will be the diameter and the length of the motor needed. Before moving on, let me answer the question. What is a phase in electrical system? Any coil carrying an alternative current is called phase. In the above example, we use three phases. Let me explain how. Let's focus on coil A. I switch it on for let's say 1 minute and then switch it off. Next, I move to the second coil B, switch it on for 1 minute and then switch it off. Then I move to the third coil C, switch it on for 1 minute and then switch it off. Now I am back to the first coil A. This time I switch it on and reverse the current for 1 minute. Again I move to the second coil B, switch it on and reverse the current for 1 minute, and once more I move to the third coil C, switch it on and reverse the current for 1 minute. You see, alternative current is generated in each coil, and each coil carrying an alternative current is called phase. So we have used a three-phase system. Now how many magnet poles and the motor phases can be used? As we have seen, to increase torque, another bar magnet is added to the center, making the total number of poles become 4. It is possible to build brushless permanent magnet motors with any even number of rotor magnet poles and any number of phases greater than or equal to 1. However, 2 and 3 phase motors are most common, with 3 phase motors dominating. Brushless permanent magnet motors have been constructed with 2 to 50 or more magnet poles, but the most common ones have single digit pole number. Since our main goal is to increase torque, we need to extend the pin magnet axially. which means that we need to extend the coil axially also. A smart, efficient and cost-effective way to extend coils wrapped on iron core is by using a long rectangular iron core projected inward on an external cylindrical ring. Each rectangular projected iron core is called a tooth, and the space between two consecutive teeth is called slot. And the cylindrical ring at the outer periphery is called a yoke. There are several ways to do the winding. One easy way is to wrap the wire on every tooth. Another method is to create overlap winding. For example, winding A using slot 1 and 4 and winding B using slot 2 and 5. Here, winding A and winding B overlap. Hence, it is called overlap winding or distributed winding. In the first case, when the winding are created using single tooth, it is called solenoidal winding or concentrated windings because each winding is concentrated around a single tooth. Now, let's construct a three-phase distributed winding using surface arc-shaped magnet. Let's say each arc-shaped magnet covers 3 teeth of the stator. Now answer me, why are we using windings? The answer is to create a magnet that can attract the rotor surface magnet. We need to make the winding covers the whole surface of the rotor arc magnet. Since the rotor magnet covers 3 teeth, the first winding is created using slot 1 and 4, 4 and 7, 7 and 10, and then finally 10 and 1. All coils are connected forming one phase, ensuring alternate north and south poles. Let's call it phase A. Phase B constructed using slot 2 and 5, 5 and 8, 8 and 11, and finally 11 and 2, ensuring alternate north and south poles. Similarly, phase C is constructed. Now, let's supply current in phase A for 1 minute. Rotor aligned with phase A coils. Now switch it off and then supply current in phase B. Rotor aligns with the phase B coils and now switch it off. Repeat with phase C. This process continues, making the rotor rotates. And this is how the motor works. If I ask you, apart from torque, what are other 2 parameters important? Other 2 parameters are speed or RPM and angular position of the rotor. Now I have a question for you. When do you say rotor shaft has made 1 revolution? And the answer is when the rotor is right back where it started, then we call it 1 revolution. In other words, rotor travel 360 degree mechanical or 2 pi radians mechanical. What is fundamental is rotor is right back where it started. Then it is called 1 complete revolution. There is also called electrical angle. And electrical 360 degree or 2 pi radians defines as, let's say, rotor start rotating from south pole and again come back to the south pole, then it has traveled 360 degree electrical or 2 pi radians electrical. In other words, if it start from south pole and go to the north pole and again come back to the south pole, then we call it rotor has made 1 complete electrical revolution. Now it is clear that electrical angle between 2 consecutive poles will be 180 degree electrical. If there is 1 pair of poles, then 1 mechanical revolution or 360 degree mechanical angle, there will be 360 degree electrical angle. 180 degrees from north to south and another 180 degrees from south to north. If there are 2 poles pair, then in 1 mechanical revolution or 360 degree mechanical angle, there will be 720 degrees electrical angle. Can you calculate it? Yes, 180 degree from north to south, 180 degree from south to north, another 180 degree from north to south, and finally 180 degree from south to north. In other words, the electrical angle equals to the number of pole pairs multiplied by the mechanical angle. As we have seen, for 1 pair of poles, a 360 degree mechanical rotation results in 360 degree electrical angle. For 2 pairs of pole, a 360 degree mechanical rotation results in 720 degree of electrical angle, which is 2 multiplied by 360 mechanical angle. Now, what is the general relationship between electrical angle and the mechanical angle? And it is very simple. Electrical angle theta E is equal to total number of pole pairs multiplied by mechanical angle theta m. We can rewrite the above equation as this. Electrical angle theta E is equal to total number of poles divided by 2 multiplied by mechanical angle theta m. Here, the total number of pole pair is replaced by total number of pole divided by 2. But I will be using the first relation, which is simple and clean, which is electrical angle theta E is equal to number of pole pairs multiplied by mechanical angle theta m. Now, if divide both sides by time, then we will get relationship between electrical and mechanical frequency. Electrical frequency omega E is equal to number of pole pairs multiplied by mechanical frequency omega m, where electrical and mechanical frequency in this equation in radian per second. Now, frequency is in radian per second, change it to cycle per second, and to change in cycle per second, divide both sides by 2 pi, then we will get frequency in cycle per second. Now, the electrical frequency Fe is equal to number of pole pairs multiplied by mechanical frequency Fm, where Fm is equal to omega m by 2 pi, and Fe, which is the electrical frequency, is equal to omega e by 2 pi. Now, it is common practice to define mechanical speed in RPM or revolution per minute instead of radian per second, and hence let's write mechanical frequency in terms of RPM, which is equal to RPM divided by 60. Why divided by 60? Because frequency is in cycle per second and RPM is in cycle per minute. To convert minute to second, we need to multiply the denominator by 60. Now, since we know electrical frequency Fe is equal to number of pole pairs multiplied by mechanical frequency Fm, here I am replacing Fm with RPM divided by 60, and now finally the electrical frequency Fe is equal to number of pole pairs multiplied by RPM divided by 60, or total number of poles Nm multiplied by RPM divided by 120. Let's call this relation as equation 4. In previous experiment, we have observed that if we want to increase the speed of the shaft, switching frequency need to increase. Equation 4 is representing the same thing. Electrical frequency Fe, which is switching frequency, is directly proportional to RPM of the shaft. Now, here is the challenge. How is the switching done? It is done by power electronics unit, which is combination of hardware and the software. And it is a fact that power electronics become more expensive as electrical frequency increases. In other words, switching frequency increases. Because of this, it is common to use fewer magnet poles, that is, reduce the number of poles for magnet to operate at high speed. However, we have also seen that torque is directly proportional to the number of poles. Reducing number of poles decreases the torque production, and therefore one must find a compromise between power electronics cost and the torque production efficiency when choosing the number of magnet poles. And with this, we have defined the speed or RPM and the angular position of the rotor. Now that we have come to the end, here is a summary of what we have discussed in this video. We have described the relationship between torque and force. We derived the motor sizing formula, which is K into D square into L. We explained the motor working principle using basic understanding of magnets and electromagnets. We discussed smart winding techniques, phases, poles, slots, teeth, and yoke. We described the relationship between electrical and mechanical angle. And lastly, we explain the relationship between electrical and mechanical frequency. Now, what is the aim of next video? We have developed an intuitive understanding of the motor working principle. Our goal is to maximize the torque with less input, specifically minimizing the current and uses of the magnets. Magnet properties and the magnetic model directly influence the torque production. In the next chapter, we will discuss magnet properties and the magnetic circuit to maximize the torque with minimal input. But what was most useful for you from this video? Please answer this in the comment box, which will take your learning to the next level, and see you in the next video.